So today we will design a dynamic programming algorithm for solving the Tower of Babylon problem, right? So have you had a chance to say at least read the question I posted? I mean, posted on the Dom Church website. Okay, very good. So have you tried to solve it? Okay, that's fine. So that's why we want to have one more problem in that we need to design the dynamic programming algorithm for solving it. As I mentioned before, dynamic programming is a programming method, right? So that said, when we see a problem like this, we have to figure it out. How can we design a dynamic programming algorithm for solving that, right? So in the previous three examples or three problems, we went through understanding the problem, right? Design a brute force algorithm, and then design a recursive algorithm, and finally recognizing whether or not we can store the intermediate results in order to reduce them and making it a dynamic programming algorithm. Okay? Uh, I think I may want to turn on the light a little bit. Is it better or worse? Okay, very good. Mhm. Okay, so let's start with understanding the problem first, right? And as usual, we will pick one or two examples, simple enough, and then non-trivial, so we can go through the steps to see how we can make it work on that specific uh, example, right? Or that specific input. Okay, so here is what we have. Okay, so here's the Tower of Babylon. Okay, so if you just Google and you will see that, okay, so here is the famous tower. They call it Babel Tower or Tower of Babylon, right? And you can see that the lower level is always larger than the upper one, right? So it means that in order to build this one, they use n different type of blocks. Okay, so let's have one block here, and they have an unlimited number of blocks they can use. So it means that we simply use as much as we want for all kind of block. So here's one block, okay? And we want to use the blocks to build up the tower. So here you have every block has three dimensions, X, Y, and Z, right? For the width, the depth, and the height. So with one type of block, how many different position we can use? Six. Okay, very good. Okay. What are they? Here's one, right? Same height. Here's two, right? And then this one is the height. So here we have the X, the Y, right? And the Z, now turn this way, you have X, Y, and Z, right? And finally here, we have X, Y, and Z. And here, X, Y, and Z. So very good. Each block can be used in 6 different positions, right? So excellent. Okay. Caleb, you got it? Okay. All right. So now, how can we find out what would be the, say, maximum height of a tower that we can build, for example, with using only one type of block? That is the input sample we have in the problem, right? So we have the first input sample has only one type of block. Okay, so now, in general, we can have n times of block, where n is less than or equal 30, right? That said, if you have n type of blocks, we really use 6n of the different blocks, right? Okay, because each block can bring us 6 different positions. Okay, and then we wanted to construct the tallest tower. The tallest tower by stacking the blocks. Okay, so now the restriction is that one block could only be placed on top of another one as long as the 2 base dimensions of the upper block were both strictly smaller than the lower block, right? Okay, so that is the requirement. All right, so now let's start with the example number 1. We have only one block, one type of block. And then the size are here, 10, 20, 30. Okay, so with this block, we can actually have 6 different positions, right? That we can combine together. All right, now, what are they? Here are the size of the block. Okay, so we have 6 positions. All right, very good. Excellent. 1, 2, 3, 4, 5, 6. Very good. Okay, so here we have, let's say we choose. Okay, that's good. You have 10, and then here you just switch them, right? Okay, so let me type it in. So we have 10, and then 30, and then 20. And now we choose the second one. Yeah, 20, and we have 10, 30, okay, and we have 20, 30, 10, and finally we use 30. So here we can say that here's the X, the Y, and the Z direction, right? So here we have 30, and then 10, and then 20. Very good. 30, 20, 10. Okay, so here we have 6 different types of blocks. We can think each of this one is a new type of block, right? And they can be used in this directions, or in general, the 6 directions only. So now we want to know what would be the height of the blocks? I mean, the tallest tower we can build. How can we know that? How can we find out that? So starting with the easiest solution, meaning that is the brute force, okay? Or in other words, we try all possibilities, okay? So what are the all possibilities we can have? The all possibilities we can have is that, okay, first, we have 6 different types of blocks, right? So if we stack them together and we want to build the Babylon Tower, right? Then how many blocks we can stack on each other at most? So the tallest tower will have how many blocks? It cannot be more than 6, right? Very good. Yeah, because even though we have unlimited number of blocks of each of this side, but you cannot stack 2 of this block on top of each other because it will violate the restriction, right? Okay, so that's it. I just want to say that here is block number 1, block number 2, block number 3, block number 4, 5, and 6. That's it. For any Babylon tower, we cannot have 2 of this type of blocks be used in the same tower, right? So that's it. Only one of them can be used at most. And then that means, yeah, okay, very good. Because of the restriction like that, okay, we cannot have a Tower of Babylon that has more than 6, right? In other words, 2 of them cannot be used. Okay? 2 of them cannot be used on the same tower. All right, very good. That is something we want to observe, right? Now, how many possibilities we can have for the Babylon Tower? We can check, right? All possibilities means that, okay, how about a tower that can have 1 block? And then a tower that can have 2 blocks, right? So how many, let me go to the next page. Okay, maybe I will just write it here. Okay, so that said, we will consider all possibilities. The first possibility is that the Babylon Tower has only 1 block. Yeah, 1 block. Okay. If we choose only 1 block, then how many possibility we can have? Actually 6, right? 1 is here, 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 right? Okay. All right. Now, you have 1, 2, 6. The second case is that how many tower we can build with 2 blocks. You cannot have 2 of the block 1, right? But we can have 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, right? And then 2, 1, 2, 3, 2, 4, 2, 5, 2, 6, right? Etc. Right? So that said, we have the possibility of having 1 to 6 blocks in the tower, right? Okay. And for each of this time, first we will check whether or not the tower we build has any violation. For example, when we have 2, if we use 1, 2, is it possible? It's not possible, right? Because they have the same value for the x. So it's not possible. So that said, first we list all possibilities and then we check for each possibility whether or not it satisfies the restriction, right? And then if it's satisfied, we simply add the height together, right? For example, I have here, let's say, 1. So here we have 120 and 2030. So I have this one and this one. Okay. So let's say I have 1, 4. Okay. I have 1, 4. Oops. One and then 4. Okay. 1, 4 is legitimate, right? Because 1 here is lesser than 20, 20 lesser than 30, right? Okay. So that means that 1, 4 is a legitimate tower. And then we can add the height together. Then we have the height of 40, right? Okay. So that said, after we list all possibilities, we verify whether or not the order does matter. Okay. When I write something like this, 1, 4, it means that 1 on top of 4. Okay. All right. So it depends on how we make the notation. Okay. So when I have a stack, I means that it's a tower, and hence the one on top will have to be smaller than the one below. Okay. Mm-hmm. All right. I mean, if you reverse the order, then you have to look at the tower upside down. That's possible, right? It's just a simple change. Okay, so that said, the exhaustive search or the brute force algorithm means that we consider all possibilities, verify whether or not it's a legitimate tower. If it is, then have the height, and finally pick the tower with the tallest height, right? So for the one with 1 block, if we choose the first one, then the height will be 30, right? If we choose the second block, the height will be 20. And then 30, 10, 20, 10, right? But eventually, this one will be bigger, right? 40. So that's why we see that the sample output is 40, right? Okay. So we can list on other possibility, but all of them are not legitimate. Let's try one here. For example, we have, here is the possibility with 3 blocks. We can have 1, 3, 5. Okay, 1, 3, 5. Let me have the facts here. Okay, 1, 3, 5. Is too small. Okay, let's see if we have to make it bigger. 20, 24, 32. Oh, 40 is better. Okay, so if we have the list or the tower that is built by using 135, we have to check whether or not it's legitimate, right? If it is, then we add the height together for getting the height of the whole tower. But is this one a legitimate tower? 1, 3. It's not, right? Because 10 is lesser than 20, but 20 is bigger than 10. So this one cannot be on top of the 3. Okay, 1 cannot be on top of 3. Okay, so looks like we have an algorithm, right? So first we have the blocks. We list all possible use of the blocks and then check on combination of the blocks in with the length of 1, 2, 3, 4, 5 until n, right? And for each of the possibility, check the legitimacy of the tower. If it's legitimate, then add the height together and choose or say keep track of the tallest tower. Sounds simple, right? Okay, sounds simple, but at what cost? The complexity of that algorithm. Okay, let me go straight to that. Okay, so the brute force algorithm, right? Check all possible stack of length 1 to n. If a stack is legitimate, then calculate the height, right? And select the stack with the tallest height or the max height. Okay. What would be the complexity? Big O what? So let's try to have the number of possible stacks, right? Okay, so here's what I have. Okay, so let me run the program here. Okay, so that's it. Let's see, in this situation, we have only 6 different types of blocks that we can use, right? And then finding how many possible situations, we can simply count the number of permutation of elements from the set of 6 blocks, right? And then 2 elements, and then 3 elements, and then finally 6 elements, right? Okay, so if we check on possibility, then we have here 1956 cases. That's a lot, right? And remember that we have only originally 1 block, and then that one can be put in 6 different ways, right? Okay, so now let's see what will happen if we have, say, 100 different blocks, meaning that we have 600 different possible direction we can use, right? So that said, what will happen if we change this one to 600? Here you are. Here are the number of cases that we have to go through, right? Is it a lot? Yeah, it's a lot. And if we run our algorithm for, say, 100 different types of blocks, it may take a year to finish the program. Okay? So that's why we don't want to use the brute force algorithm, right? In fact, the complexity we have here, as you may expect, that is exponential, right? Because combination, permutation, if you have, say, 6 elements, right? And you have already 6 factorial different ways to shuffle the 6 different blocks, right? So even the last one, even so here we have to the n. It's exponential, right? Why? Because here, even for a permutation of 6, meaning that we have 6 different blocks, right? We just list all possible situation, that is 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 6, 5, and then 1, 2, 3, 4, 1, 2, 3, 5, 4, 6, etc. Right? So even for this one, it's already 6 factorial different case, right? Okay, and that said, if you have n elements, then it's about 6n factorial at least, right? Even for the simplest case. So that said, the complexity for the brute force is already exponential. So we have an algorithm, but nobody wants to use it, right? So we have to throw it out. So now, let's see, how can we design a better algorithm in the sense of breaking the big problem into the smaller problems and try to solve the smaller problems first, right? Okay, so here we will try to work out this example in the following way. Okay, let me remove this one so I can write. Okay, so now we will try to find out which block can be put on another block, and then other 2 blocks and other 3 blocks, etc. Yeah. So first, when we have this one, you can see that this list is somehow already sorted, right? Because here you can see that we sort with respect to the x values first, right? If the x value are the same, then we sort with the y value. Similarly, the x, the y, and then the x value, the y, the 20, and then 30, and then 10, 20, right? So first, this list is sorted with respect to x and y, right? We don't want to sort z because we don't use z direction for deciding whether or not one block can be on top of the other, right? Okay, so here's what we have. And actually, that is why we have this example. The example here, 10, 20, 30. Yeah, because the input samples is, say, selected for showing you that, okay, what you need to do. Okay, so in this situation, you already have the list here is sorted. But for the second example, you will see that the list is not sorted and we have to perform a sorting algorithm. But it's simple. You already learned many different sorting algorithms, right? Okay, so now we have the list of 6 different blocks from one original block, right? So here, let me write it like this. I have 1, 2, 3, 4, 5, 6, and then I have 1, 2, 3, 4, 5, 6. And now I want to create a table. And in the table, I will have row I and column J telling me whether or not the block I can be put on top of block J. Okay? So that's why I have 0 here on the main diagonal, because you cannot put 1 on 1. Yep. 2 on 2, you cannot. So that said, I have a table. It's a Boolean table. It will give me 0 or 1. 0 means, for example, in this case, block 2 cannot be put on the block 2, right? So now I will try to fill out this table first. Okay, can you give me the values? So let me do it for one row, and then you will finish the rest. Okay, so here 1, 2, right? Okay, 1, 2. It's a 0, right? Because 1 cannot on top of 2. Okay, 1 cannot be put on top of 2 because the x here are the same, right? So same thing for 1, 3, 1, 4, 1, 5, 1, 6. They're all 0. Same thing, 2, 1, 2, 1, 0. Okay. Finish the table and tell me at what row and what column you have a 1. The table here are all 0 except one cell. I think I did too fast. Okay. Okay, so what do you have for all of the cells here? They're all zero, right? Yeah, they're all zero. So for example, 61, 61, 30 is bigger than 10, right? 62, 30 is bigger than 10. 63, 64, 65, they're all zero. Okay? So where do you have the one? Column 6, row 3, okay? Here you have the 1, 3, 6, 3, 6. Yeah. 20 is smaller than 30, 10 is smaller than 20. Yeah, very good. Okay. So here you have 3, 6. Okay. 3, 6. Okay. Anywhere else? One, 4. 10 smaller than 20, 20 smaller than 30, right? So I think previously I wrote it 0, right? It's not correct, right? So here we have 1, 4. Okay. Okay. Anything else? So here we have 1, right? 1, 4 is 1. 2, everything would be 0, right? Because you have here 30, right? 3, you have 3, 5, nope, 10, right? And then 3, 6, right? 4, here you have 30, so nothing, right? 4, you have 30, so it will be nothing. 5, 30 is clearly nothing, right? Same 6 answer. Okay, so you have 1, 2, 1, 3, 1, 4, 1, 5, no, 1, 6, 0, right? So here you see that we have to fill out the table, right? But what will happen if we sort this list in the reverse order and we start from the first row? So in that situation, we need to fill out only half of the matrix, right? But the total number of steps are the same, still big O n square, right? So that said, if we start from 1 and then we go down, but if we start from 6, here, meaning that we sort this list in the reverse order. If we start with 6, meaning that is the biggest one, right? Then we know that everything here should be 0. So we don't even have to fill out, right? Because we know everything here should be 0 if we start from 6. And then 5, right? So we don't have to go up. We just have to fill out this value, right? Same thing here, okay? Okay? But it's the minor thing, right? We can sort this list with respect to ascending or descending order. It saves us a little time, right? Okay, so now we have 2 cells. In that we have the 1. So now, how can we find the, say, tallest tower based upon this table? This table tells us about which one can be put over which one. Right? That's why I call this over. Okay, this one is the position. So here I have the position of the blocks, right? So X, Y, and Z here. For original block, we have 6 different positions, right? So that's why I named this one position and this one over. Okay, very good. So now, how can we find out the tallest tower? Okay, sum up the Z value. Okay, but how? In this situation, it's simple, right? We just have 1 here on this row and 1 here on this row. In other words, we only have the value 1 in 1 row and the value 1 in, okay, I mean, in different rows, and then the value 1 on different columns. But the next example will show you that we may have many ones on the same row and many ones on the same column. So in that situation, which one should be added? Okay, so in this situation, you can see that, yeah, we can stack this one on top of this one, right? That means that for these 2 blocks, we simply have the height of what? 4 is 30 plus 10 is 40, right? And then here we have 3, 6. 3, 6 is also 40. So we can either build the Babylon Tower by putting 1 on top of 4 or 3 on top of 6. We have 2 different ways, right? And hence, we can have the tallest one. But it's not really an algorithm yet. So the idea is as follows. If we look at the blocks from bottom up, okay, so I want to look at the block from bottom up, or as I mentioned before, we can sort the list with respect to X and Y in descending order. Then we have this list in the reversed, right? Okay, so now let's start with the last one, the 6. So we will try to consider the following list. First, I try to see if here is what I call the tower. The tower list. So first, I want to know if I6 or I just want to say that this one is the 6th position, right? So I can use either I6 or simply 6. Okay, let's say P6. For P6, what would be the height of the tower in that P6 is on top of the tower? So the idea is as follows. I want to know what is the tallest height of a tower in that P6 is on top of the tower. And then what will happen if P5 is on top of the tower? And then P4, and then P3, and then P2, and P1 finally, okay? Okay, so let's start with the first one, P6. If P6 is on top of the tower, what can we tell about the height of that tower? The tallest height of any tower in that I have P6 on top. Remember that P6 will have the biggest value when we sort with respect to X and Y, right? Not at least, actually, at most. Why? Because if P6 is on top of the tower, can we have anything below that? No, we cannot, right? So that's why I go bottom up, okay? So P6, we know that the tallest tower we can have is 10, right? Now, what will happen if I go to all of the tower with P5 on top of the tower? How can I find the tallest tower in that P5 is on top? At the beginning, I know that P5 has the height of 20, right? So I have the height of 20. Okay? But then what will happen or what can happen? I will have to see when P5 is on top, can I have anything below? How do I know? Look at the table, right? So if P5 is on top, can we put it on top of what? If we have a 1, meaning that P5 can be put on top of that, right? So here we have nothing. So the tallest tower is 20 only. We cannot add anything more, right? Okay, similarly for P4, we have nothing, so we have 10. Okay? Now, let's go to P3. P3, at the beginning, that block has the height of 30, right? Then we need to see, okay, P3, right? Can it put on top of anything? P6, right? So the tallest building starting from P6 is 10, right? So we have 30 plus 10 is the tallest one. If we have P3 on top of the tower, right? So here you can see that if we have many number 1 on this list, then we have to go through them and then look back, check which one will give us the biggest value for the height and put it here, right? In this situation, we have only one, number 1. So meaning, okay, starting with P3, below P3, we cannot have P2, P1, P3, P4, P5. P6 is the only thing, right? So that's it, because we cannot put P3 on the other blocks. So we still have the height is 30. The only block we can put on is the P6. So we look up the P6, right? And the biggest or the tallest height is 10. So we have it here, add them together, and now we have it P3, right? Similarly, for P2, it has nothing. So we have here 20. And P1, right? We have 30. And now we have to check. P4 is 10. So we add 10 here. Right? So that's it. The biggest value we have 40 here and 40 here, right? So we can have either of them as the tallest height of the Babylon Tower. Okay? Got it? So that's it. We go up here and then we check, okay, what will happen if we have this P6 on top of the tower, right? And then P5 and then P4, right? If this one is on top, then we have to check the rows here to see, yeah, This one can be put on top of one. If we have a one, then we have that one on top. Then we just simply go back and then add that value in, right? So if we sort this one like this, then when we go down here, we only look up at the value before, never look up at the value below, right? So that is the idea. And once we understand the idea here, we can design our recursive algorithm as well as the dynamic programming. Okay? Any question? Okay, sounds good. No question, then here is your hands-on practice. We need to have example number 2, right? So in this example, we have 2 original blocks with the size of 6, 8, 10, 5, 5, 5, all right? So follow the same, say, procedures I showed you before. Fill out the position table, sort them. You can sort with respect to descending order. And then after that, we will try to have the table to, we call the over table. Can we put one over the other? Okay. All right. So here, 3 minutes. To fill out the table here, sort that, put it here. Okay, so I guess it's simple, right? All right. Where are the 555? You have to put all of them into one table because any of them can be used. Okay, so here you have 6, 8, 10, right? So then the next one would be 6, 10, 8. Easy, right? Okay. So similarly, you put it here, put it here, put it here. Caleb has the correct one. And then we have the next original block has the sign of 555, right? So with 555, how many different positions we can use? Only one, right? So that's it. In total, we have 555. In total, we have the set of 7 blocks that we can use, right? So if you have 555, then we don't swap anymore because even if we swap the Y and Z, we have the same block, right? Okay, got it? So that's why when we have the same values, we have to remove the duplicates. Okay, so that's what we have, right? And then after that, we have 8, 6, 10, right? This one is already sorted, right? But this one is smaller. So what we may want to do is that either we sort with respect to ascending or descending, right? So let's see here we have 8, 6, 10, and then 8, 10, 6, and then 10, 8, and 10, 8, 6. Now, when we sort, right, we can sort with respect to the, say, descending, meaning we want to bring the biggest one up. It's up to you, right? We can either have it ascending or descending. Let's say if I have the descending, then what will I have? So I have 555 here, right? It's too bad. Okay, and then I have 6, 8, 10, 6, 10, 8, right? 8, 6, 10, 8, 10, 6, and then 10, 6, 8, 10, 8, 6, right? So I just have this one on top. Yeah. All right, so let me copy this so I can have it on the next table. So now we have to build up the over table. Let me put it here so we can use it. Okay, can you see it? Little bit hard to see. So okay, so here's something better, right? Okay, so here are the values, right? And now we build up the table. Tell me where you have the 1, real quick. So 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Where do I have the 1? Okay, so that means that we have 1 here, right? Anywhere else we have the 1. I have here, yeah, 4, 6. Anywhere else? Just fill in the table, right? We can go bottom up. So here is what I have, right? So this one and this one. Okay. So that's it. Check it by yourself at home for all other values. But the only place where we have 1 is, yeah, row 2, column 5. Row 2, column 5. This one. 6, 8. Okay, so here I have, say, 1. Okay. Okay. Row 2 and column 5. Okay, 6, 10, 6, 8, 8, 10. Right? Okay, good. Q5, 1. Right? Anywhere else? How about 4, 7? 4, 7. Right? So row 4 and 7. Okay, so here we have 6, 8, 6, 10, 8, 6, nope, right? 8, 10, yes, right? And then 10, 6, nope, right? Here, okay, we can go up. You see what happened? Same thing, right? And here we have same, so smaller but bigger, right? Smaller but the same, right? Okay, 6, 10, 10, 6. Okay, so same thing for this one. We have 8, 10, 6, okay, 10, 8. So we have 4, 7, right? And then here we have 8 cannot, right? Go up, we have nothing, right? Go down, we have 10, 6. Nope. So here, nope. Okay. So this one, nope, because we have the same thing, right? So that's it. We have 1, 1, and everywhere we have 0. So now, based upon the idea I explained to you before, find out the tallest tower. Okay. Find out the tallest tower starting from, say here we have P7, meaning what would be the tallest tower in that I have P7 on top of the tower. And then we have P6, P5, P4, P3, P2, and P1. So P7, okay? The height is 6, right? Can it be put on top of any other cells? Nope, right? So that said, the value of the tallest tower with or any sub tower in that we have P7 on top is 6, right? Because the height is 6. P6, same thing, we have no only 0, so we have 8 here. Okay, P5, same thing, we have 6. P4, okay, at the beginning we have 10, right? And then it can be put over the 7. So we just have to look at 7, we have 6. So this one will be 16, right? Is the tallest tower we can have with P4 on top, right? Okay, same thing for P3, nothing. So this one we have 10. P2, we have P5 on top, P2, 10, right? We have P5 on top, P5 is 6, is 16. Finally, P1, we have 5, okay? But we have 1 on everywhere. So that said, we have to see P5 plus P2, P1 plus P2, P1 plus P3, P1 plus P4, P1 plus P5, P1 plus P6, and P1 plus P7, right? So the biggest value we can have is from here, this one, or this one. So either case, we have 21. Okay, so that's it. 21 is the tallest Babylon tower we can build based upon this kind of blocks. All right. So what you have to do is that write down the procedures I explained here to you as a pseudocode, right? And then try to see if it works by submitting your solution to DOM-Church to see if it works, right? And then I will post the solution once everybody have a chance to write down the solution, yeah, or write down the source code. Okay, so time is over. Any questions you have? Okay, no question. That's good. Then just take care. Okay, bye-bye.